When a blacksmith strikes a glowing piece of iron, it bends and flattens, but it refuses to shatter. We rely on that unique combination of strength and flexibility every time we drive across a bridge or turn on a light. Our ability to work with these materials is predictable because we understand their internal structure, and the path to that understanding actually started thousands of years ago in India. These baked bricks from the Indus Valley civilization are early proof of that expertise. To produce these in such large numbers, ancient builders had to master chemical heating processes that were consistent and repeatable. You can see even more advanced chemistry in the Ajanta and Ellora caves. The artists here created paints and resins from plants and minerals that are still vibrant today, showing they had mastered complex recipes long before the arrival of modern science. Around 600 BCE, an Indian philosopher named Acharya Kanada took these observations a step further. He proposed a huge conceptual leap, that everything we see is built from tiny, indivisible pieces. He called these units paramanu. He described them as eternal spheres that are always in motion, essentially defining the smallest possible unit of matter over 2,000 years before the idea took hold in the West. Kanda's insight changed the target of science. It was no longer enough to look at how nature behaved. Now, thinkers were trying to find the tiny, hidden particles that made it happen. In 1808, John Dalton brought this idea into the modern era. He published a framework that turned the study of these tiny particles into a formal science. Like Kanda, Dalton realized that matter is made of indestructible atoms. They are the building blocks of everything, and they are never created or destroyed during the chemical reaction. Dalton's main rules added a layer of precision. He showed that atoms of different elements have different weights, and they always link up in specific, fixed amounts to form more complex substances. While Dalton's solid atoms were a major step forward, they left one mystery unsolved. How can a solid block of atoms let electricity flow right through it? To answer that, we had to look even deeper at the moving parts inside those atoms. If we look at the elements in the center of the periodic table, the ones we rely on for their toughness, like iron, copper, and zinc, we see materials that handle heat and pressure differently than anything else. These metals are incredibly strong and require thousands of degrees of heat to melt. That durability is the result of a very specific type of microscopic connection. Imagine the metal atoms as spheres, packed into a tight, organized grid. In most materials, the electrons stay stuck to their specific atoms, but metals play by different rules. In these metals, the outer electrons let go of their parent atoms. They begin to drift freely through the entire structure, filling the gaps between the spheres. This creates a sea of electrons. When the metal is hit or bent, the atoms can slide past each other, but this electron sea acts like a flexible glue, holding everything together so the structure doesn't snap. Because the atoms are packed in a grid, the metal is strong, but because the electrons can move like a liquid, the metal is conductive and flexible. Because those electrons are already moving freely, they can carry an electrical charge from one end of a wire to the other almost instantly. This microscopic movement is what makes large-scale production possible. In this factory photo, you can see how copper is processed into miles of wiring, the invisible network that carries power to every home. Iron atoms pack together in an even denser pattern. This gives iron an extremely high melting point and a natural stiffness that allows it to hold its shape under heavy loads. You can see that strength at work in this iron bridge. The way the atoms are locked together allows these arches to support the weight of a train without the metal cracking or collapsing. To understand modern chemistry, we need all three pieces: Kanda's concept of the building block, Dalton's rules for how they combine, and the sea of electrons that gives metals their unique power. It's a reminder that the technologies we use to build the future were first imagined by thinkers who lived thousands of years ago. If you want to see how these building blocks explain the rest of the world, subscribe to ChemAura. And don't forget to join our WhatsApp channel for study notes on everything we covered today. See you in the next lesson.